about all things sort of data center and grid connections. But before we get into the fun details of all that, I wanted to ask you my favorite question, which is what is your favorite vacation spot?
Vacation spot. Well, I think I'm gonna have to go with Vancouver Island. I have friends of the family who live up there, and not necessarily everybody's first choice for summer destination, but the water's warmer than California, and the scenery is unmatched.
All right, I could believe that. I love a good island destination that's maybe not the Caribbean islands, but a little bit more out in the woods. All right, cool. Well, we'll jump in here. To kick off and sort of set the stage, but I'd love to start with the basics. So when people say it's getting harder to connect new data centers to the grid, what is actually going on?
There's really, I think, two things that are feeding into that. One is that there is a lot of stuff that needs to get connected to the grid, and that's been getting progressively harder over the last few years. Some things that have been driving utilization of grid capacity include onshoring of manufacturing. So people are building factories, people are putting in EV and fleet charging facilities, people are expanding existing manufacturing capabilities, and electrifying existing industries. And those have all driven up demand for grid connectivity. And so we started to see a couple years ago that this was driving an increase in overall grid demand. Demand on the grid has been flat for more than 20 years within the US. But starting probably 2 years ago, we started to see like a couple percent and then 5% and then even 10% year over year growth in some grid locations. So, firstly, there's more people who want power, and infrastructure can only be built so quickly to both generate and connect them to it. The other thing that's happening is that data centers are suddenly a lot bigger than they used to be. And so the constraining factor for data centers to be able to be developed, built, connected to the grid is availability of power at this point. Now, this is something that was true a long time ago for the hyperscalers. Back when I was at Google, power availability was the biggest constraint for building a new data center because we were building 10 times larger than anybody else in industry. So, everyone else was building like 10 to 20 megawatts. We were building 1 to 400 megawatts. And now suddenly everybody wants 1 to 400 megawatts. And there's only so many places where there's 400 megawatts or a gigawatt available on the grid without making pretty significant changes.
Very cool. And I'd be curious. I feel like when people talk about grid constraints, there's a lot of different pieces that may feed into that. So as you're thinking about distribution grid capacity, transmission grid capacity, generation availability, like what are the pieces that really start coming into that? And are there ones that you're seeing that are more prevalent, or does it really just depend on the region?
So I think firstly, all of the above are definitely constraints. We've been hearing for a long time about limitations in transmission grid availability. And that is really related to the need to interconnect more generation. But on the other side of generation is load. And so if we're short of grid for connecting generation, we're short of generation, firstly. And then we're also short of the network capacity to connect it. On the distribution side, there haven't been as significant capacity constraints as we're starting to see now. And the reason for that is that the distribution grid tends to be a little bit more overbuilt because it's a little bit less actively monitored and and it's generally more radial. So capacity to a particular location, you can just kind of build that out and then you have more capacity. Whereas on the transmission grid, you need to think about the interactions of the entire network, kind of serve a broader set of network needs. So those are all definite wins. But the other one that's really started to change is that in the past, if you were a large load that wanted to connect to the grid and get power, you would go talk to your utility or even to your ISO and say, like, hey, I'm a large load. I want to connect to the grid. I want to get power. You might then go and procure power contracts in the form of PPAs from suppliers. You might procure power contracts in the form of RECs from suppliers in other regions, and bring that along as part of your overall power supply arrangement because there's so much load coming online and there is a lack of capacity overall to serve that collective need. They're being asked to bring capacity that is connected to the same grid as the load in order to build the load. And that is new because that's not just buying a REC. That's like arranging for somebody to build a power plant.
Yeah, it sounds a lot more difficult. And it also, I think it ties to this question that's maybe in the back of folks' minds from time to time of like, why is it so difficult for us to be able to just build out more infrastructure? Like we've built the grid over, the last decades to 100 years, but is it more people? Is it technology? Is it cash? Like what is making it harder to just like turn the tap on and get a whole lot more grid capacity out there?
Well, I think that that previous observation about the fact that there actually hasn't really been a lot of load growth in the last 20 years is a big part of it. We've certainly been improving the grid, adding things onto the grid, updating the way that it works, but we haven't really added a lot more capacity in a very long time. And so, that's not just a matter of like making a new plan and building more. That's also kind of reawakening organizational muscle around dealing with scale, getting creative around constraints, thinking about how to plan ahead of load. Because in general, grid expansion is fairly reactive. Um, we might plan ahead for 10-year load growth and put in place a plan to go ahead and build out the grid to meet that 10-year need. But a lot of this load has been showing up in a, 1 to 2 year time horizon. For the grid, that is lightning fast. That is tomorrow. And those time delays on changing plans, getting updated load plans, getting, equipment in place to meet that need in a short-term time frame, nothing is built for that. The planning processes are not built for it, the supply chains are not built for it. And so there's a lot of constraints on how quickly we can add that capacity.
Makes sense. And I think one of the topics that's come up a few times when it comes to this, the various different options that we have to help accelerate data center interconnections, especially, there's things like, are folks going to have their path to power go off grid? Is the path to power going to be to just like find the perfect place where there is enough capacity today? Or are there things that are kind of in the middle? And flexible interconnection is a topic that has come up a little bit as folks are starting to look at this. And I'd be curious for your take. Like, what is flexible interconnection and how is it different from what utilities or data centers are used to today?
Yeah, so I think firstly, there's two different ways that you can think about flexibility on the grid. The first of those is being able to reduce demand in response to a signal. So you could think about one kind of flexibility being like demand response, where in times of constraint, you might ask some grid users to reduce their load a little bit. There's a bunch of limitations in how we use demand response on the grid today, but the biggest one is that that mechanism is really only applied to loads and facilities after they've been connected to the grid. So if you wanted to come in ahead of time and say like, "Hey, I'd love to plug in this load, and I'm occasionally willing to turn it down if there are times when the grid doesn't have enough power or when we need more network capacity." There's no way to have that conversation today. What happens instead is that the new site being added is assessed at its full nameplate capacity. So if it comes in as a gigawatt data center, it's gonna be assessed as a gigawatt data center, even if the initial plan is only building out 100 megawatts of capacity or 200 megawatts of capacity, or it's looking to build out over the next 10 years. The current planning process still needs to account for that full allocation. And so that means that we have to really build out ahead of observed need in order to fit that planning process. Whereas we could both move faster and get a lot more efficiency out of our grid if we were able to be a little bit more flexible about that. Especially to say, like, either this load steps up over time or it can sometimes be reduced in times of additional need. The other axis of flexibility is thinking about how we get the grid capacity, and by which I mean the poles and wires and transformers and substations lined up to be able to plug these assets in. And so you could think about this as being like really two things. One is energy supply, the other is the physical network of the grid's ability to deliver that supply to the places where it's needed. And those can have different constraints on them. And so when we think about flexible interconnect, that can either be plugging in with an agreement to reduce demand sometimes, or it could be plugging in with an agreement to perhaps use less of the physical carrying capacity of the grid than the full nameplate capacity of the facility. And that could be as simple as saying, like, look, I need 100 megawatts of load. There are 60 available. I will just power the rest myself with solar storage, generators, natural gas plants, whatever. So both of these are ways to think about flexibility. The other one that is really coming up a lot is the idea of taking data centers entirely off grid. And there's a subset of developers that are seriously exploring this and are building out facilities that look like that. That's really difficult for a couple of reasons. One of them is that it can be really expensive to build enough generation to supply an entire gigawatt data center from on-site generation. And a couple of other really big considerations around that are limitations on local emissions. So if you're going to put in, 100 megawatts of natural gas or even worse, diesel generators, there's a local emissions problem associated with that. And that's not a small consideration, right? Like that's something that the neighbors might have to deal with for quite a long time and really impacts kind of health and permitting and all of these sorts of things. The other issue there is that the reliability profile of only on-site generation is linked to the reliability profile of the site. And it kind of limits your ability to bring in power from other areas if there are issues with the equipment on site or with the connections on site. And that's not generally the case when you're bringing in power from the grid. And so there's issues with reliability, there's issues with environmental impact, and there's issues with cost for doing this on site. And the last one is also just you still need to order a lot of equipment, and that equipment has delays. The back order backlog for like GE's turbines apparently is running at 7 to 8 years right now. And also the substation equipment required to move power from generators to data centers, even on site, is also pretty back ordered. So it's not necessarily faster either.
Yeah, and I feel like it's the goal of all this is to be able to get the grid and the data center connected faster so that the data center could be running sooner. That doesn't necessarily address the main problem there. So,
Yeah, that's right.
okay.
And that's where getting creative around finding connections to the grid and getting started sooner and thinking about laddering that up over time can be a much quicker path to getting a site up and running.
Okay. I think it might be helpful too to address what is sometimes the elephant in the room when talking to data center developers of they hear flexibility and grid and connection and all these terms. And the idea of flexibility is tied to turning down their servers and to putting their customers offline. Can you help clarify, like, is that a requirement for these kinds of interconnections or is that not true?
So it's definitely not a requirement, although it is potentially part of a solution set. One of the biggest ways that people have been thinking about flexibility is by adding batteries alongside the data center site, where the batteries can serve load and take load off the grid some portion of the time and provide that site level flexibility. Another way that people have been thinking about this is putting in generation, but it is also certainly possible to reduce load on the site itself. And that is something that, depending on the kind of work being done at the data center, may be part of the option set that folks are interested in exploring. So, like back when I was at Google, one of the biggest concerns that we had for thinking about how we operated Google's globally distributed kind of data center scale systems was actually making sure that we got as much utilization out of those data centers as we possibly could, because they're really expensive assets. All work being done in that kind of company requires using them. And a lot of the ways that we tend to use our computing assets leave them sitting idle a lot of the time. And you don't really want, your multi-billion dollar assets just sitting idle. And so we did a lot of work on optimizing, making sure those were used as much as possible, making sure that there was as much capacity as possible available to serve user demand at the time and place where it was needed. And the last thing that we wanted to do was be turning down those servers for extraneous reasons like, grid power supply. But we had the tools to do it. And hyperscalers, as a user class particularly, have the tools to do it. It's really more of a business consideration as to whether or not they'll choose to use it. And so if your choice is not build the data center or build the data center and promise to curtail sometimes, that may change the calculus in terms of thinking about the options that are in front of you. The other one that really comes up is that it depends a lot on the type of load that the data center is serving. So if you have an AI training load, you might need to use a lot of compute capacity at a certain time. But you may not be as sensitive as to exactly when. It may be fine to move it around in time a little bit. If you have a non-training load, a set of work that is like just serving user requests, whether that's AI inference workloads or just regular web serving workloads or things like that, you're going to have a diurnal usage curve. So your computers will do more work when people are awake using the internet, and less work when they're asleep and not using the internet. And so there is also opportunity to use those, you know, natural kind of axes of flexibility within the load of the data center to provide some more grid facing optimization. It's just not something that has been um, a top business consideration, I think, for the industry until pretty recently.
Thank you. And when talking about flexibility and this ability for the data center, whether they're using a generator or a battery or compute flexibility to shift what is the net power demand from the grid, how does that actually work in terms of the like what gets communicated between the utility and the data center? And can you touch a little bit on what that looks like?
Yeah, so one of the biggest challenges with doing this today is that that mechanism doesn't exist in a large scale, scalable, replicable way. This idea of making these large loads be flexible has been baked into relationships between utilities and large loads for a long time. But in the past, that's traditionally taken the form of enrolling them in demand response programs, which are very manual. Most demand response programs will call events maybe if just a few times a year. And when they say call an event, they mean like call you on the phone. Like call up someone at the facility to be like, hey, next Tuesday, it's going to be really hot. We want to turn our grid usage down. Please plan to reduce your grid usage. And that's fundamentally not scalable to the data center world. Firstly, there's a lot of them. Secondly, there's often nobody on site to take a call. And that's not really how the facility is managed either. And so if you want to kind of transpose that idea of being able to flex load to meet a grid need, you really need to kind of update the communications paths and technology that we use to firstly understand like when would that be needed? We might need to do it a little more often. It might not be twice a year, it might be twice a week. And then you need to be able to communicate that automatically to the data center. And that is not really something that we're entirely equipped to do from a grid scale perspective today. It's not hard from a technology perspective, or at least we have the tools that we need to do it, but it's new.
So how does Camus look to fill that role? Like what is kind of the mechanism that you envision that would be a more scalable, effective approach?
Yeah, so the technology that we originally built was software for understanding grid needs, particularly around loading and power quality and grid conditions, and being able to translate that understanding in a large scale, scalable way to being able to dispatch assets, help them work together, tell them, please turn it down a little bit. We need to use some more grid capacity. Kind of all of these ideas around orchestrating loads to help them better fit within the limitations of the grid as it stands and to better take advantage of power supply when and where it's available. And so this is still really an orchestration challenge, right? Except the things that we need to orchestrate are a little bit bigger. So instead of telling EV like, please charge after midnight or a solar facility like, hey, we need you to update your volt var curve to address voltage issues, which you might do, as part of a DERMS program or dealing with residential assets, or even enrolling them in a virtual power plant program and calling on them sometimes for demand response. What we're really doing here is saying like, we can take this understanding of capacity, need, and availability on the grid, synthesize that down into a signal for an individual site, communicate that to the site, and enable the site to work transparently within grid constraints. And so that's what we do when we work with a site to flexibly interconnect it, is we basically provide them with the signaling to help them understand what the grid needs. And then we monitor those sites and communicate back to the utility if they want it to understand what the assets are doing, but we're basically hiding the complexity of that interaction from the utility and from the grid. So the utility can just focus on operating their grid and doing what they do best. They don't necessarily need to control and, monitor and dig into the innards of every single asset. They can just kind of keep, interconnecting things roughly the same way, but with a little bit of an addition from the site to help them manage it dynamically.
Thank you. And then from the utility side, we commonly hear this question of what happens if a data center blows past the limit the utility has set to them? Or like, what is the fail safe that the utility operator can trust to make sure that this is all going to work?
Yeah, look, I don't think anybody really trusts software alone to manage the physical limitations of the grid. So, one thing that I like to kind of remind folks is that trust is not necessarily something that happens between people when you're talking about the grid. It's a property of the system design. And so utilities have a very reasonable desire to make sure that, even if we are managing things with data and communication, that there's a hardwired backup that can provide protection in the case of a problem or somebody not listening to a signal or there just being some kind of emergency where they need to take an action. And so typically what we see for these sites is that utilities will want to add some kind of hard shutoff for the site. For smaller distribution connected sites, that can be something like a switch that implements, there's an emerging standard called UL 3141 that will do this for kind of smaller sites. For larger sites, it could be, a switch or recloser or even substation equipment that can shut the site off in time of need. But nobody's going to do any of this. Like think about connecting a site flexibly or maybe even at all without tools to be able to switch it off in case of trouble.
Okay. And I imagine that the operational paradigm for this is not a binary of like it's all running and it's perfectly fine, or we have hit the big red button and everything is off, and that there's this kind of cascading approach to reliability. Is that how you see it? Or I don't know, drawing from kind of your Google times, are there eaches that seem to be best practices for how to manage those kinds of flexible resources?
Yeah, look, when I was at Google, I was running teams that were in on-call roles that, were monitoring operations 24/7 and would be called to intervene in case of critical problems, system emergencies, et cetera. And so when you're in that kind of operations function responsible for overall system health, you typically you want a few tools at your disposal and you want those to be somewhat layered, right? You have a set of tools and information about the system that helps it to operate in steady state. Certainly for the systems that we ran, a lot of that was automated or, could mostly kind of run itself. You have a set of tools that you might use normally in case of things like an outage or needing to do scheduled maintenance to shut off a portion of the system. And then at that point, you need things like basic capacity planning to know that the rest of the system can take over the load, these kinds of things. You want tools to be able to communicate limits to individual participants, and be able to have them, be good actors within the broader system. And so, that's true for utilities today, right? Like even if it's just communicating demand response events to participants or being able to potentially reach out and shut off something through the meter if there's an issue with preserving quality of service, those kinds of things. And then you want a big red button in case all of that stuff fails, right? So it's kind of it's a defense in depth approach. It's all of the above, really.
Yeah, the big red button seems like an important at least piece for peace of mind for an operator.
Every operator loves a big red button. The times you end up using it are actually incredibly rare in most of my experience, but every now and then you really need it, and it's important to have it there.
So that makes sense for the utility operation side. For a utility transmission planner that's listening in or thinking about this, how do they know how much flexible capacity is really there on their grids versus the firm capacity? And is this just like a huge complex analysis project for them, or how do they actually figure that out?
Yeah, I do think that this is a challenge in the space today, and part of that's a tooling and a data problem. There's a set of really nice tools in market today to do an interconnection analysis that basically takes kind of the nameplate rated capacity of a facility and then look at how that would interact with the grid at a point in time. And planners will typically choose, a couple time windows that will include like peak utilization or for, solar facilities or generation facilities, perhaps minimum utilization. Um, and then they'll model that, and then they'll look at potentially a couple contingencies, failure conditions, those sorts of things. And that's great if what you're trying to do is plan for the worst case scenario and then build physical infrastructure to make sure that even in the worst case scenario, your system is going to be okay and that it won't cause unusual failures or out of plan failures and that you can handle contingencies. That's great. But that does mean that you need to build a lot of infrastructure to support any particular asset. And it means that a lot of times that infrastructure is sitting idle. So if we want to get more value for our money out of the grid that we've built, and we want to be able to serve more load with the grid that we've built and will build, then being able sometimes to thoughtfully use that additional capacity is really helpful. But you do need to be able to think about not just a point in time, but like every point in time. And that's where the tools today don't really help planners to do that. So one of the things that we've found to be really important in helping to have this conversation with utilities and with developers is to be able to supplement those interconnection tools and studies with time series based analysis so that you can look at it over, every point in the 8,760 hours of the year or even over 10 years to understand like over a 10-year period of time, if you were to put in an asset and think about managing it flexibly, how often would you need to curtail it? How much flexibility would be important to being able to place this asset? If you did have a contingency, what would that look like? And could you get the asset to respond to that in a timely fashion? And if you did, what would you need it to do? And so that just requires tooling and access to data in a more flexible way that's hard for most utility planners to get to today. But it is absolutely something that can be added alongside traditional mechanisms that will help them to be able to answer those questions effectively.
So do utilities have the data they need today to do that kind of 8760 planning analyses, or does that require, more data, more monitoring, more devices out there to kind of pull that in?
They absolutely have the data that's required today to do this from a planning perspective. Pretty much all utilities at this point are working with digital grid maps, digital connectivity models. Most utilities have decent SCADA setups that are bringing in data about their grid, their substation equipment, all of these things. Most also have smart meters at this point that you can use to understand aggregate system load and think about, even what the collective load profile of the system looks like. It can be a challenge to get all of that data together in one place. It can be a challenge to interact with it flexibly and to think about using it in different ways because our existing tools tend to be really specifically focused on answering like one type of question. It can be a lot of work to marshal that data and clean it up because typically when you're running something like an interconnection study, you already need to do a fair amount of data cleanup just to get, the model cleaned up and running, to make sure that you've got the right time step for running, especially if you want to look at multiple data types together, multiple data sources together. It needs to be from the same moment in time, or at least correlated for the analysis. And doing that over a time series analysis can be really challenging just from a data marshaling perspective, because time series naturally have gaps. Equipment won't collect during some windows. There might be times when the system is atypically switched, and then you need to kind of figure out how to deal with that. There's just all kinds of challenges in using data over a period of time. However, these are also things that we have good technology solutions to, and these are the sort of classes of issue that, during my time at Google, for example, we did a lot of work on building monitoring systems and analytic systems that could deal with this sort of time series data challenge and be able to think about, perhaps running 10,000 analyses in parallel over a source data set. And so there's tools that we can use to clean up that data, to make sure it's aligned, to make sure that those models will run and be able to put the results back together. And this is something where I think software can be really helpful, but the data is there. The place where that's a little bit less true is for ongoing real-time operations. It's fine to synthesize an understanding of grid state from meter data for planning purposes, because you're basically just running a model, forecasting what the conditions might look like. But when you're actually running these facilities in real time, what we've found working with utilities is that it's really helpful to just add a few more data sources. And that can be as simple as just like dropping in some line sensors around a facility that's going to be flexibly managed, putting in a better meter for that facility, putting in some additional SCADA points that you can pick up to just tell you, okay, this is what line loading looks like on this particular feeder line. Like, these things are not a big addition, and you don't have to do them across the whole grid, but it's really helpful to add them when you are looking to add a facility that's gonna be flexibly managed to make sure that you have enough data to do that effectively.
Got it. Right. Maybe one question that speaks to the here that's come up as a source of flexibility from or a source of skepticism from time to time. Where is the market at for this kind of flexible data center topic right now? Are there any utilities that are actually offering flexible grid connections for data centers or flexible connections like overall? And how can a data center or utility look to the market to see where this is going?
Yeah, so this is a pretty fast-moving topic within the industry at the moment, and there's a couple of things that are going on. Firstly, just the general idea of a flexible interconnection, like a connect and manage kind of scenario, is something that folks have been introducing in the utility space. So, like ERCOT has a connect and manage tariff for generation. In Australia, curtailable load and curtailable generation is kind of just becoming the standard model for connecting new assets to the grid. In the UK, connecting loads, with a requirement for flexibility or network supporting curtailment is also something that people are starting to do in a widespread way. And so we're also really seeing this begin to be introduced in a widespread or programmatic way for US utilities as well. And there's a bunch of utilities around the country that have introduced or are introducing flexible interconnection tariffs and programs where you can go and have a conversation with them about, hey, like, I want to connect to the grid. I'm willing to be a little flexible. Can we reduce my costs? Can we speed up my time to connection? Can I fit if I couldn't fit before? And so there's probably about 10, 15 utilities around the country that have programs that look like this. PG&E and SCE both have flexible interconnection programs. ComEd has been going through a pretty active process to put one together. There's a bunch that are looking at it. For data centers, this is a new idea. And that's really because up until, probably about a year ago, firstly, data center demand was not growing nearly as quickly. The sites weren't necessarily as big, maybe a year or two ago. And there were fewer of them. It's been part of the overall trend towards connecting large loads in general alongside factories and onshoring loads and stuff. But the idea that you might need to do something really creative to get that stuff powered is becoming an increasingly large part of the conversation around data centers, and the reason for that is just that everybody's really in a hurry to get more capacity built out, and so this kind of folds into, a sense of urgency around getting more AI capacity, being able to support innovation within the US for AI technology, but also, quite frankly, just supporting a really rapid growth in very, very large scale computing challenges within the broader industry. And AI is one example of that, but it's not the only one. So this is a new idea for data centers and for very large loads. And like I said, there's precedent for it for thinking about flexibility after it gets connected. The big change here is talking about flexibility before it gets connected as part of the interconnection process rather than after the fact as part of a demand response program.
Okay. Maybe to add a little color here, zooming all the way out, why should data center developers and utilities want a flexible connection? What's in it for them?
Yeah, I think this is such an interesting time for our industry because we have this unprecedented challenge of needing not just a little bit more grid capacity, but maybe 10 times as much grid capacity as we currently need. And we've known this was coming. We've been talking about electrification for a long time. But I think that the extent to which data centers are driving that and how quickly they're driving it has taken people by surprise. And if we meet that need the way that we have traditionally met needs for increased power and increase grid capacity. What we're going to do is take the nameplate capacity of every data center that signs up for an interconnection agreement and build that much generation. And when we do that, we're probably going to overbuild generation by potentially quite a bit. and overbuild network capacity by potentially quite a bit. Because every data center developer that's showing up in queue asking for a gigawatt is generally asking for it for a site that they're going to start at 100 megawatts, maybe expand to 200, maybe expand to 400. And they want that gigawatt so that they know that when they eventually need the capacity down the line, if they need it, that they can expand that facility without having to start the whole process over. But they're not necessarily planning to show up with a gigawatt of load on day one, or even within the next like 2 to 5 years. It might be a long time, it might never come. If we assume that everything in queue shows up at its rated capacity and then we build generation for it, especially if it's fossil generation, but also just more generally, we're going to probably overbuild by quite a bit. And that is going to be tremendously expensive for ratepayers and consumers. There's no way really to pass along all of that cost only to the data center developers because it impacts every single part of the grid. Every single part of the grid would need to be updated to do that, and that may well still happen anyway. But by being thoughtful and introducing flexibility to the equation when we connect these loads, we give ourselves the ability to do things like defer capacity build out until later. We could wait and see what shows up and plan for that collectively. We could make sure that we're actually kind of building a bit ahead of demand, but not necessarily, 10 times more than is needed. And we can also introduce some tools that operators can use to help take better advantage of the times and places where power is more available and put it to work in places where people need it. And so when we add data centers, if we add them with a bit of on-site flexibility, it increases our ability to use cheap renewables. It increases our ability to move load around in time. It increases our ability to get more out of the network that we have. We can increase the efficiency of that. But ultimately, it just makes it a lot easier to pay for all of this. And so we really need to be accounting for that now because it's at the moment of interconnection that you can have that conversation. We're really going to struggle to have it later. We need to be thinking about this right away.
I see the vision for how data center flexibility can contribute to a more efficient, a more affordable, a more hopefully reliable grid. I'm curious if you were to go talk to somebody who's, I don't know, maybe mid-level at a data center developer or someone who's like a manager at a utility who's excited about this idea. But they have to go to their CFO and be like, what's the one way this is going to help our company? What would be the one thing you would tell the data center person? What would be the one thing you would tell the utility person?
Yeah, on the data center side, overwhelmingly the biggest consideration is speed to getting facilities built. If you go talk to a hyperscaler, they will tell you that their top three considerations for building new facilities are speed, speed, and speed, which is actually a direct quote. So anything that they can do to get to power sooner is going to be really critical to them as a business. In a lot of cases, they're not actually very cost sensitive. They'd be willing to pay more if they could connect sooner. But also in a lot of cases, like, there's just only so much physical equipment you can get and get installed and get built within a certain amount of time, no matter how much you pay for it. And so being able to get some grid power now and more later, maybe more off grid generation later as part of the mix, thinking about being creative with using what we have is the quickest way to get power, into the ground and into facilities as they're getting built. And that is what matters most to data center developers. On the data center side, the whole story here is speed. On the grid side, I think the biggest story is really being able to enable utilities to say yes to these facilities, get them onto their grid, get them scaling up in place. While there's an opportunity to think about, placing them within a particular utility's territory, there is a bit of competition between utilities. A lot of facilities, a lot of data center developers have projects in multiple queues. Utilities generally are pretty excited to get kind of large, predictable loads in place, because it helps them to both build more efficiently on their grids and also make more money. And so the opportunity to get these facilities placed is important to utilities. It's a really nice opportunity, and it's a strong need as well. Utilities want to serve their customers. It's really important to them to do so. So if they can be a bit flexible or ask for a bit of flexibility on the data center side, they can also get that done for their customers more quickly, more cheaply, more effectively, that keeps rates low for everybody, that helps the utility to fulfill their mandate to provide power. And those things matter a lot to utilities. They're really important within the utility.
So last question, I know we're right at time here, but you've talked about it a little bit already, but to put it to, I think, a finer point, where exactly does Camus come into all of this vision?
Yeah, we were originally founded with the intention to bring software and data technologies to support orchestrating the grid. And at its heart, that's really about getting power from the time and place where it's needed, where it's produced, to the time and place where it's used. And that means being able to make better use of the wires that we have and the substations, equipment that we have, means being able to make more efficient use of the generation that we have, to be able to take advantage of cheap renewables, to be able to meet that demand without building quite as much infrastructure. And this is still an orchestration problem. It's just that the components being orchestrated are a lot bigger than I think the industry was originally envisioning. This is not rooftop solar anymore. This is like industrial size facilities. This is factories. This is gigantic data centers. And it's also the generation that's going to be built to serve them. We need to get those things matched up. We need to make the most efficient use of resources that we can. And we also need to do that while decarbonizing our power supply and decarbonizing our grid. Ultimately, that is part of the long-term vision for the sector, and it is really important to preserve a path towards that. The grid has always been the heart of that vision, using the grid to be able to connect sources of demand to what can eventually be clean sources of supply. That has always been the goal. So, when we started the company, it was with the idea of being able to leverage, the data that's out there today that utilities have, put it to work to manage assets connected to the grid to solve all of these problems. And that is still what we're doing. But as a company, we have really started to realize that it doesn't really matter very much if you're orchestrating rooftop solar if the biggest driver of need on the grid is 100 megawatt or a gigawatt data center. Being able to actually, like, think about having those loads participate in active management of the grid, it's really important to fulfilling that long-term vision. And the technology that we built is fundamentally geared to support scale and to be able to solve these problems at both small and large scale. And so we're really good at understanding the grid, synthesizing grid needs from a wild variety of complex data sources, do a lot of the data marshaling that is needed to solve these challenges, and to be able to help multiple parties kind of interact with that information about what the grid, what will work, what's going to be most effective and efficient, and fundamentally be able to help everybody get more out of that grid as an asset. And so when we today are tackling challenges around orchestration, this really looks a lot more like working to get stuff connected to the grid, helping to really facilitate that conversation about connecting assets flexibly, both on the utility side, helping the utility understand how to do that, and also on the developer side, helping the developer to understand how to do that. But then also being around and being able to help with operationalizing that connection across the longer term. So we really see our role as being able to be the glue in that interaction and facilitate those two sides coming together to be able to meet that larger need.
Thank, thank you very much.